Hi everyone, for today's lesson we are going to learn about how to graph absolute value functions with transformations, with our learning objective being that I can graph an absolute value functions, or I can graph absolute value functions and I can describe transformations from the absolute value parent function. So we're going to be comparing everything to a parent function. The next learning objective is I can write equations of absolute value functions given a graph. So these are all of the different ideas that we are going to learn about in this section. So the first thing I want to talk about is the parent function of an absolute value function. It is the simplest form of the function, which means that there's no pluses or minuses. And in this case, it is f of x is equal to the absolute value of x. Remember, f of x is just a very fancy y. And whenever we are talking about transformations, we are always going to be comparing to our most basic function, our parent function. The ordered pairs that we use, we allow our x values to start from -2, -1, 0, 1, and 2. And what that means is we are going to substitute -2 into this function. So the absolute value, remember, always makes whatever goes inside of it positive. So absolute value represents the distance that a value is away from 0. So -2 is 2 units away from 0, so our output would be 2. So the absolute value of -2 is 2. The absolute value of -1 is +1. The absolute value of 0 is 0, the absolute value of 1 is 1, and the absolute value of 2 is 2. And once again, this just represents distance away from 0. 2 units away from 0. So what we're going to do is we're going to take these ordered pairs and we're going to plot them on our graph. So I'm going to plot -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. Now, if you need to pause the video to get yourself a straight edge, please go ahead and do so, but you're going to want anything that is straight. So I just have like a pad right here to provide me with a straight edge. And I'm going to connect this V using my straight edge. What's really cool about absolute value functions is that the shape is a V, absolute value. It's a lot of fun. So anyways, here is our absolute value graph. And this graph has a vertex, which a vertex is that bottommost point or that topmost point. It's our maximum or minimum of a function. And in this case, it has a vertex that is located at 0, 0. So this is known as our vertex. The slopes, we'll call it slopes because if you look at this function, it is like a piece of a line, and over here is another piece of a line. As you get further into your education, you'll learn that absolute value functions are what we call piecewise functions, but the slopes of each piece are going to be +1 and -1. So we have on one side, if we were to start at our vertex and rise 1 and run 1, we would land at another point along one side, and same with the other side. The graph opens up in this parent function, and the domain is what we call all real numbers, which is a symbol where you draw the number 11 and then write the letter R with the second one. This represents the language of all real numbers. And that's because the domain represents all of the values of x that this function touches. And since we have an arrow pointing to the left, that means that this function would continue forever and ever into the negative direction, and our x values are negative to the left. So all real numbers, or all values of x starting at -infinity, going all the way to the right, we have an arrow. All values of x to the positive side are included all the way to +infinity. And what I'm writing down right here is what we call interval notation of how we express all real numbers. I have parentheses around them because it indicates that we will never truly reach infinity. And I'll talk about that a little bit in greater detail in just a moment. The range represents all of the y values that this function touches, and in this case, there are no y values down here that are being touched until you reach the vertex. And at this moment in time, the y value here is 0. And then because we have arrows pointing up, that indicates that our range is all values of y greater than or equal to 0. Or if we were to express this in interval notation, our range starts at 0. It is included, so I'm going to put a bracket around it, going all the way up to an arrow that goes straight to infinity. So that is from 0 to infinity. So once again, this is called interval notation. This is one way to express a range or a set of numbers that represent a domain in a range. In this, whenever you see a parenthesis, that indicates that the circle would be open, and therefore whatever values that we're talking about are not included. And we use a parenthesis around infinity because we will never truly reach infinity, so therefore it's always an open circle. A bracket means closed or included. A closed circle. And I'm going to write included as well. So this is something that I need you guys to know. So if you happen to have a highlighter, this is important information that I would recommend that you know and study and make sure that you understand. When it comes to expressing your domain and range, I am very open. If you feel comfortable with using inequality symbols, I'm very comfortable with that. Or if you want to use interval notation, I'm cool with that too. I really don't care as long as it's accurate. Now, if we want to talk about how this parent function changes, we call that a transformation or transformations of the absolute value parent function. And to describe those transformations, we use a general form of an absolute value function known as y equals a times the absolute value of x minus h plus k. And these a, h, and k values affect different elements or characteristics of an absolute value function. So the first thing we're going to explore is the effect of a. Now, whenever you are graphing y is equal to a times the absolute value of x, notice that that a is like the coefficient of that absolute value. In this problem, notice that we do not have an h and k, which means that our vertex is going to remain 0, 0. So it's always going to be located at 0, 0. Instead, our a value affects how the graph opens. It affects the opening of the graph. So depending on what characteristic a is, depends on what the graph is going to look like. So for example, if the absolute value of a is bigger than 1, that means that the graph has been vertically stretched or elongated. And the graph of a times the absolute value of x will be a narrower graph than that of y equals the absolute value of x. It will be narrower than our parent function, so you would expect that your graph would be relatively skinny compared to our parent function. In terms of description, we would call this a vertical stretch by a factor of a. This is the language that you would use whenever you are asked to compare a transformation to the parent function. So it says for a is the absolute value of a is less than 1. That means that our a value is going to be like 1/2 or 1/3. And that means that the graph has been vertically shrunk. We call that a shrink or a compression. And the graph of y equals a times the absolute value of x is going to be wider than that of the parent function. And so you would expect to see your graph be fairly wide. The language that you would use instead of vertical stretch, you would use shrink instead. This is a vertical shrink by a factor of a. Now, if your a value is equal to -1, that indicates that we have a reflection in the x-axis. A lot of times we use the language, a reflection across the x-axis. And that just means that your absolute value graph is flipped upside down. And so this is for a be equaling a -1, or even if a is just simply equal to a negative number. That will indicate that we have a reflection. And then once again, if you see that your a value is equal to 1, then that means that there is no vertical stretch, shrink, or reflection taking place here. It has the exact same width as the parent function. So you would just expect it to be a normal v. Just completely normal. So what does our a value mean? So this means that when we multiply by a number on the outside, it affects the slope. And more specifically, it affects the slope of the right-hand side. So our a value, if you ever wanted to have a little trick that'll help you with graphing these, the a value is the slope of the right-hand side of the graph. That is something I really want you guys to know, because this is what we are going to use whenever we are graphing. A value is the slope of just the right-hand side of the graph. Now, when we multiply by a negative number, doesn't have to be -1, any negative number, then that means that the graph opens down. So those are two things that I really need you guys to take away from the value of A. So in this example, we have y is equal to 1/3 times the absolute value of x. The first thing you're going to do whenever you are graphing these, let me zoom in just a little bit so that you can see this a little bit further. All right. We always want to start off by identifying what our vertex is. And in this case, our vertex is located at 0, 0, and our a value in this case is equal to 1/3. So I'm going to start by plotting my vertex, and remember that 1/3 is the slope of the right-hand side. So I'm going to start at 0, 0 and rise 1 and run forward 3 units. Now, one of the cool things about absolute value is that it's reflective. It's a symmetrical graph where we have reflected points on each side of the vertex. So if I have a point that's 3 units away from what we would call a line of symmetry when we get into the next section of this unit, I can count simply 1, 2, 3 units on the other side, and I have a reflected point. Now, all you need in order to graph an absolute value are 3 points in order to create a very nice, lovely V. So I'm going to make a comment right here. All you need are 3 points, including the vertex, to create an absolute function or absolute value graph. So all you need are 3 points, including the vertex, to create an absolute value graph. So that is something that you need to know. So I have my 3 points. That's perfect. I'm going to use my straight edge to draw my V's, or each side of my V. And now what I'm going to do is a thing called compare. And so whenever you see compare, that means that we're going to be talking about what we notice and how it compares to the parent function. In this case, my a value is simply 1/3. And so the language that we are going to use is that we have one transformation in which the graph was vertically, this was a vertical shrink because my A value is 1/3. This is a vertical shrink by a factor of 1/3. And that is the exact language I'm going to be looking for whenever I assess you on any quiz or test or any homework assignment. I'm specifically looking for this particular language. In example number 2, we're going to do the exact same thing. We have a vertex that is located at 0, 0. My A value is located at -2, and so I'm going to plot 0, 0, and then remember that this A value represents the slope of the right-hand side, so I can go down 2 to the right 1, and I can reflect that point on the other side of what we would call a line of symmetry that we cannot see. And if you would like to have more than just 3 points, you can keep going with your slope. I can go down 2 to the right 1 and then reflect that across the line of symmetry. I think it's nice to have more points than just 3. I'm only requiring a minimum of 3, but it's nice because you can get a really lovely V and not miss any points. All right, so then our transformation in this problem, we actually have 2 transformations taking place. The first transformation is this negative symbol. That negative symbol means that we are going to have our graph reflected across the x-axis. And the second transformation is the number 2. That means that the graph is skinnier or stretched compared to the parent function. So whenever you see a negative A value, that means that we have 2 different transformations. First, we have a reflection across the x-axis. And the second transformation is that we have an A value that is 2. So we call that a vertical stretch because it's skinnier, it's bigger than 1 by a factor of 2. Notice I did not use -2, and that's because the negative was already addressed in our first transformation. So this number right here, whenever we're talking about vertical stretches or shrinks, is always going to be positive. And so maybe to emphasize that when I'm talking about this language up here, maybe I need to put absolute value of A on the outside so that we recognize that that value always has to be positive, and we can tear apart a negative A value into 2 transformations. All right, let's go ahead and move on to the next page. Now we're going to talk about the effect of H and K. So notice I've taken the A value out, and now we're just looking at the graph of y equals the absolute value of x minus h plus k is the graph of the parent function in which it has been translated. Translated is also known as a shift. H units horizontally, which is our left, right. And k units vertically, which is going to be up, down. All right, let me zoom out just a little bit so you guys can actually see the whole page. All right, hopefully that'll zoom out just a little. All right, so the vertex is always going to be located at HK. So notice that it's not a negative H, and that is because H is always the opposite of what you see. So if you see a minus H, a positive H is going to be used in your vertex. And K is exactly what you see. And that is because we have CA plus K. Notice we have a positive K. It's exactly what you see. This statement right here of H is the opposite of what you see and K is exactly what you see is something that I say a lot in this class. This is something I need you to know because it is a concept that we will use over and over and over again in this class. So what this means, it means that if you were to add a number on the outside of the graph, that means that we're talking about K. That means it means the graph is going to move up. And that's because K is located in the Y position, and Y is your up and down, or your vertical axes. And if we were to subtract a number on the outside, so minus K, that means the graph is going to move down. And this makes sense. These are our K values, and it's exactly what you would expect. You would expect, you see plus, you go up. You see minus, you go down. So this is exactly what makes sense. However, if you were to add a number on the inside, the graph, instead of moving to the right, would go in the opposite direction. It would actually move to the left. And if we were to subtract a number on the inside, we would think left, but it's the opposite. We would move it to the right. So these represent the transformations of H. And whenever you are thinking on the inside, it's always opposite. So I want you guys to think opposite. Think opposite of what would make sense. All right, let's go ahead and look at number 3. Number 3, we have y equals the absolute value of x minus 1 plus 3, in which this case our vertex is going to be located at, it's the opposite of what I see, so the opposite of a minus 1 is a positive 1, and exactly what I see a plus 3, it's a 3. So there's my vertex. My A value in this case is an invisible number 1. If you can't see it, we assume it's 1. So I'm going to plot 1, 3. And from here, I'm going to apply my slope of the right-hand side by rising 1 and running 1 and reflecting it on the other side. Rise 1, run 1, and reflecting it on the other side. If you want, you can just kind of do opposite slope if that helps you. And now I'm going to use my straight edge to draw each side of my V. It is really important for you guys to draw your V's or any graph in this class where it extends the grid, because a lot of times we analyze beyond just maybe this little tiny V. So I know that some of your teachers in the past may have thought that it was okay to just have your graph be this tiny thing. In my class, I absolutely need you guys to extend across the entire grid. In this problem, we have ourselves one transformation. The width is fine. We don't have to talk about A. A is 1, so there is no stretch or shrink to even talk about. But we do have this 1, 3. So there is only one transformation, and we call it a translation. 1 unit to the right, so 1 unit right, and 3 units, it went up, 3 units up. And I'm comparing it to where the parent function was supposed to be. The original vertex was supposed to be at 0, 0. So I'm just talking about how it translated. That is it. That's our only transformation. Let's go ahead and look at example number 4. In this problem, our vertex is going to be located at, well, I see a plus 2 on the inside, and on the inside it's always the opposite of what I see, so that means my H value is negative 2, and my K value is exactly what I see, so that's located at negative 5. My A value is once again the number 1. It's an invisible number 1 on the outside of the absolute value, and now I'm going to plot these points. I'm going to plot negative 2, negative 5. And then I'm going to apply my slope of 1. So I'm going to rise 1 and run 1 and reflect that point on the other side. Rise. And I like I said, I like to have multiple points. So I'm just going to keep going until I can't anymore. I just think the graph looks a lot nicer. And I'm going to draw my V. Each side of my V, make it very lovely. Voila. And now we're going to talk about the transformation. And in this case, once again, there's only one transformation because our A value is a positive 1. And so we're going to call this a translation. Two units. And in this problem, it went to the left, 2 units left. And 5 units down. So to recap what I taught you in terms of graphing functions in the form of y equals a times the absolute value of h plus k, a few things that I need you to know when you're comparing it to the parent function. Number one, there is a reflection in the x-axis if our a value is negative. There is a vertical stretch if the absolute value of a is bigger than 1, like a 3 or a negative 4. All of those values are bigger than 1. There is a vertical shrink if the absolute value of a is in between 0 and 1. So I want to kind of emphasize that. It doesn't have to be just less than 1. It needs to be in between 0 and 1. So I'm looking for something like 1/2 or 1/3 or 2/3, something to that effect. It's going to be in between. And then there is a translation, left or right, h units, and up or down, k units, depending on what you see. Notice that the letters R, S, and T are highlighted, and that's what we call an RST description or transformation. So you might hear the language of RST or PFRST as we go, and I'm going to talk about that a little bit more in later lessons. All right, so the next couple of examples, it says pair and solo, and that is something that we are going to discuss the next time I see you. You'll either work with a partner or you'll work on your own on these problems. If you want to do them right now, you're welcome to, but this is going to be a discussion for next time that I see you, putting all of the pieces together. All right, next we have example number 5. And example number 5 says, write an equation for the graph shown. Now remember that whenever we're looking at our graph or trying to come up with an equation for it, we really need 2 pieces. We need to know what the vertex is, because that's what we used whenever we graphed. And in this case, our vertex is located at -1, 2. Our A value, if we were to look at the slope of the right-hand side, it appears that these points that are on the right-hand side have a slope of rise 1, run 1 of 1. So therefore, our equation is going to be y is equal to, I'm not going to put an A value down of 1. You can, I won't mark you down, but simply the absolute value of x, and this is always going to be the opposite of what I see for my h value, so x plus 1. And then exactly what I see for 2, so plus 2, and there's my equation. Once again, I have a pair and a solo, and that is something that we're going to discuss next time I see you. You're welcome to try it on your own and be prepared for discussion, but you do not have to. So the next thing I want to talk about is a solo, and I just want to at least get you started with this idea where it's asking you to write an equation of the absolute value with a reflection in the x-axis. And so that means something. It tells you something about that equation. A vertical stretch, this tells you something about the equation. And a translation so that the vertex is located in the 4th quadrant, which means that you have a vertex at x negative y, or a positive h value and a negative k value. And the thing that I want to talk about really quick here is this idea of 4th quadrant. Just as a recap of what you learned in Algebra 1, there exist 4 quadrants. The first quadrant is always where x and y are both positive. This is known as the first quadrant. The second quadrant is where you're going to the left for your x values, so you have a negative x value, and your y value is positive, so negative xy. The third quadrant, we always go and counterclockwise, is down here. And that is where x and y are both negative, because you have to go to the left and then down in order to reach ordered pairs in this quadrant. And finally, we have the fourth quadrant. And the fourth quadrant, you're going to the right with your x values and down with your y values. So that's why it is x comma negative y. And being able to come up with your own function is really important. There's going to be a lot of create your owns in this class because I want you to be able to take what I'm teaching you to the next level. That is the end of this lesson. If you have any questions over anything, please feel free to email me. Otherwise, I hope you have a wonderful day.